recording, and these recordings get posted on the YouTube channel of the UMBC Center for Social Science Scholarship, and there's a good chance we'll have it up by tonight or tomorrow. So before we go any farther, I'll just say regarding our seminar series, if you're interested in other seminars in this series, you can go to ges.umbc.edu, and you go to the home page, click on Department Seminar Series. You'll see other seminars in the series. The ones that have already happened, we have links to the YouTube recordings. Here's today's seminar. We'll put up the YouTube link once that happens. And then we have a series of other seminars scheduled over the remainder of the semester, so you can see what some of those topics are if you're interested. So just go there if you want to hear more about that. We're already lining up seminars for the spring semester now that we've got the schedule settled for the fall. And I just want to say a word about our next seminar next week, just to point out the flyer hasn't gone out yet. We wait until we're done with today's seminar. But next week we have a faculty member, Dr. Yusuke Kuwayama, who's in the School of Public Policy. He'll be talking about integrating hydrologic and ecological models into economic analysis of water resource policy. So you can look forward to that for next week. Join us same time, same place. We will put out this announcement after Jeff's done talking today. So some of you may have read some of Jeff Halverson's articles in Capital Weather Gang, where he often dissects recent extreme weather events. And it's been an extraordinary year, as you all know, and as Jeff is going to talk about with us. And to introduce Jeff, I welcome Tyra Cobb-Davis, who's first-year graduate student in our program. So Tyra, take it away.
Hi, and good afternoon, everyone. Today I have the honor of welcoming our speaker for the day. Dr. Jeff Halverson is currently Professor of Geography and Environmental Systems and Associate Dean in the Graduate School. As an expert on severe storms, in 2001, he helped pioneer a new aircraft-based upper atmospheric measuring system to take direct observations in the eye of hurricanes for NASA. He and his team of grad students conduct research on thunderstorm, electrification, nor'easters, and severe weather warnings. Halverson teaches GES courses on weather and climate change, severe storms, and natural hazards. He is presently working with scientists at NOAA's Ocean Prediction Center to study extratropical and tropical transition of ocean cyclones, and is a regular writer for the Washington Post Capital Weather Gang. He worked with researchers in GES and Curie to understand the generation and impacts of the Ellicott City flash floods in 2016 and 2018.
Thank you very much, Tyra, Andy. It's so heartening to see such a great crowd of interested people. I really want to thank you so much for your attendance today. I have just switched over. You should see my colorful opening PowerPoint slide. I'm titling this talk Summer of Floods. And I think I should append it to say Summer and Autumn of Floods, because these keep on going. And so we're going to examine a spate of these things in the past 6 months around the globe and try to understand where climate change may be factoring in, where other things may be factoring in to accelerate the hydrologic cycle. So the outline of my talk is I just want to give a very brief overview of what we mean by the multifactorial nature of flash floods.
Jeff, I want to interrupt you just a second. You're not in full screen mode. Can you put it into full screen mode? Just go to the bottom right icon that shows the screen. The next one.
Okay. How's that?
Oh, no, now we're looking for center mode. All right, go back to where you were. That was better.
Yeah, because I'm using
running two screens. Yeah,
I'm using dual monitors, and it's tricky.
Okay,
so,
all right, go ahead.
Okay, so we're going to review 3 events in China, Germany, and Italy. We're going to review 3 events here in the U.S. We're going to try to synthesize these a bit and draw some climate change connections. And then the ultimate question we want to end up with is looking at how do we better prepare and warn people for these events. So as you heard in the introduction, I did a lot of work on the Ellicott City flash floods in 2016, 2018. I'm not going to discuss those floods here, but we were part of a multi-perspective panel on these events. We had a seminar over in Curie where we brought in meteorologists, climate scientists, hydrologists, engineers, interested faculty, students, members of the community to discuss the how, when, and why, and try to constrain how to mitigate these in the future. But what I really want to get to is, and this is very, very important, folks, flash floods are ubiquitous natural hazards, not just the United States, but around the world. And these are very multifactorial events. And it's not just meteorology. It's not just meteorology. You can have a rain event that's designated 500 year in terms of return interval, and you have to separate that from the flood response, the hydrologic response. Whether that turns out to be a 500-year interval flood has to be assessed kind of independently, okay? But we have the meteorological factors, and sometimes it's not so much about how much rain, but how fast the rain is falling. It's the rain rate and the capacity of the ground now to infiltrate, process all that water. And so that gets into susceptible natural landscapes. You might have a very steep walled catchment that's going to cause water to flow at high velocity. You may have previous rains, antecedent rains in the weeks or months prior that are going to render the soil saturated. So the sponge essentially is already soaked, okay? Or you may have some modifications, folks, that are anthropogenic. This is land use change, and it's been going on for decades and decades, and we see this all around us. We see the replacement of natural vegetated surface with impervious surface, and it's not just asphalt roads and concrete parking lots, it's rooftops as well. And you have channelization, and you have systems designed to convey large amounts of stormwater, but sometimes those systems get overwhelmed or create larger problems in areas that are adjacent to the stormwater management system. So the idea behind flash floods is that there's a lot more here other than just the meteorology. I'm focusing on the meteorology, but it's good to have this framework in mind. So let's go and take a brief tour, if you will, of these deadly and even catastrophic events. And we'll go to Europe, July 12th, 6th through the 16th of the summer. We had tremendous flooding, and it hit Germany and the Netherlands extremely hard. At least 242 fatalities from these floods. 196 of those were in Western Germany. Other countries involved: Belgium, Romania, Italy, and Austria. And I'm going to show a graphic that illustrates kind of the weather system involved here, kind of two scales of motion. There was a large perturbation in the jet stream that became stagnant for almost a week. And then there were thunderstorms embedded within the warm side of that jet stream disturbance. And so what you had was a combination of what became an aerial flood, river flood, and a large area flood with embedded periods of flash flooding. Peak rainfall amounts 9 to 11 inches of water generally within a 2-day period. And it includes one account of 8 inches in a 9-hour period in Reiferscheid, Germany. Let's look at some pictures of where exactly this rain fell. This is the bullseye. This is the 48-hour summation of rainfall. And of course, the Europeans are very fond of using millimeters. So you have to do the quick math in your brain. But as I said, generally 9 to 11 inches. And you can see how focused this is in these particular regions of Germany. Moving on to some views here. This is, when you send up drones and helicopters and light planes afterwards to look at the damage, it's rather appalling when you get the big sweep like this. And dramatic rescues were in order. I mean, this clearly is likely a flash flood that's gone on here. And here you see an urbanized region with, this looks a lot like Ellicott City, doesn't it? It kind of reminds me of Main Street with these interconnected rows of buildings down either side. And this is just, when you look at this, you see the energy of the water involved. You see axles of vehicles intertwined with large uprooted trees and just all manner of debris tangles and jumbles of material. Here's another view. Once again, kind of looks like Ellicott City, and this is exactly how Ellicott City appeared in the wake of this event. It was just a muddy trail of wreckage everywhere through cities and towns in Western Europe. This is the meteorology. So this is the jet stream, and the blue area indicates a large vortex. We call this a cutoff low. It is a low that gets orphaned from the rest of the jet stream, which is displaced far to the north and just kind of meanders of its own accord. And on the eastern side of the low, because it's a counterclockwise flow around the low, there is a very, very warm, unstable humid air that's been sourced in the Mediterranean, and it's being pulled up and over portions of Western Europe. And this was a pattern that repeated itself for many, many days, and there were embedded thunderstorms in that plume of moisture. So moving along, we're now looking at Changsha, China, July 20th. The area in central China, we had 33 fatalities, up to 3 million people impacted. And now we start to see higher rain rates, 12 to 16 inches in a 24-hour period. Get this, in one location, 8 inches of rain in 1 hour, 8 inches of rain in 1 hour. This happens to be the heaviest rain rate ever observed in China from the sources that I could depict. And once again, we had large synoptic weather systems, including the approach of a typhoon, which is a large low pressure vortex, and a large area of high pressure adjacent to that, working together to pump a very moist, unstable plume of moisture up out of the South China Sea and the Western Pacific, and also combining with orographic uplift. Here is the map that shows the foci of the floods. You can zoom out and you see this area of central China. You can see how the South China Sea moisture input comes into play here with an approaching typhoon and high pressure system working together. And zooming in, you can see the area of most intense accumulation. And once again, millimeters, so 300 to 400 millimeters of rain, which is 30 to 40 centimeters, which is well over a foot in some spots. I find this is a very interesting diagram. This is a time series from a location in Zhangzhou, and this is a 36-hour time series. Every hour, there must have been a tipping bucket or a recording accumulating digital gauge. Every hour you can see the rain totals. And look at how in the center of the event, we have this phenomenal 8 inches per hour spike. And that type of rain, folks, can only be delivered by very, very intense thunderstorms. So once again, thunderstorms are the crucial deliverers of these phenomenal amounts of rain in a short period of time. Here's some pictures in the aftermath of the flood. And just like Ellicott City, you see just, stacks and stacks of vehicles piled up on top of each other. And these type of pictures abound everywhere on the web. And now what I want to show here is another extreme event that just occurred very recently. This is the 4th of October now, and this is Italy. You can't see Italy. It's kind of hidden beneath all of this color, but all this color denotes rain accumulation amounts. And this was a phenomenal. Let me see here. Yeah, I seem to have lost the slide that describes the overview of this rain event. This is extreme roads that are turned into rivers and sidewalks turned to stream. This is taken from a video cascading rainfall. The amount of rain in this event was absolutely phenomenal. It was 36 inches in a 24-hour period. 29 of which fell in a 19-hour period. And this ended up being the absolute heaviest rain rate ever recorded in all of Europe, through all of European history. And the focus was a low pressure system, once again, pulling in a plume of extreme high humidity values out of the Mediterranean. This is a depiction of what we call precipitable water in the atmosphere. And this precipitable water was 250% above what we consider typical for early October. And there were just thunderstorm after thunderstorm complexes embedded, moving over the same areas. You can see from satellite rendition here, one complex after another. And this goes on for a full day over a lot of the northwestern portion of Italy. And you can see in this diagram down here, all of the lightning strikes that were detected on the Italian peninsula. And there's well over 500,000 strikes here that occurred in a 24-hour period. So once again, thunderstorms embedded in really, really intense moisture plumes, setting up this phenomenal flash flood. You know, the idea of 29 inches in the space of 19 hours, I can't fathom that. That is just unbelievable. Now, moving here to the United States, here we have something that made the news, New York City, July 8th, remnants of Hurricane Ida. Now, Ida was a storm, almost a Cat 5. It was a Cat 4 that hit Louisiana. And poor Louisiana has been battered by over half a dozen tropical cyclones in the past 18 months. It's just been horrific what's happened down there. They just keep coming in off the Gulf of Mexico. So Ida comes in Louisiana, does a number in terms of wind and storm surge and heavy rain. But then there's kind of a very deadly second act that unfolded as Ida moved up into the Appalachians and moved up into the Northeast over Pennsylvania, New York. And a devastating series of floods were generated across New Jersey, across parts of far western New York State, Long Island. And we had, believe it or not, 57 fatalities, folks, in the Northeast. And this is many more people died up there from this second, third day flooding than as a result of the landfall in Louisiana itself, which is really, really a sobering commentary that you have to be really careful of these tropical cyclone remnants. And there was a cloudburst of 3.2 inches in 1 hour in Central Park and in Newark, New Jersey, that really overwhelmed and surprised a lot of people. And the situation we had here was a remnant low circulation with the remnants. Just a tropical depression was all that was left of Ida, but interacting with a stalled frontal boundary and some jet stream energy that were pre-positioned over New York State, Pennsylvania, and New Jersey. And that's what brought this system back to life. There was an additional energy source of uplift that helped rejuvenate the storm. And so these are images from New York City. We had 13 fatalities, folks, just in New York City alone. And a lot of those fatalities were in basement apartments that I believe that no one really understood the extreme vulnerability to flood. When that occurs in that setting, there's no way you can get out. And so you see the cars here. This is absolutely what you don't want to do, right? Get yourself in a lot of trouble. And these are more images in the immediate aftermath. Let's look at the rain accumulation map here. And you see the totals, 8 to 9 inches, the epicenter of really, really heavy rain in the vicinity of New York, Newark, New Jersey. And here is kind of the setup, the meteorological setup. So here's the remnants of Ida working its way up the Appalachians. And this large canopy. The colors here are radar returns from thunderstorm echoes, large canopy of heavy rainfall across New York, PA, New Jersey. And here is this front that was pre-existing and now combining with the remnants of Ida. And you see that this circulation was pulling in a plume of moisture off of the North Atlantic. And North Atlantic waters in the west part of the ocean basin are very, very warm, late September, early October. So there's lots of evaporation. It's very, very humid air. And so there was this river of moisture flowing in, very unstable air. So in the green scalloped area is where a lot of convective cells, a lot of thunderstorm cells were firing off. Now, let's turn our attention to Waverly, Tennessee, August 21st through 22nd. This is 60 miles west of Nashville, to try to put it in geographic perspective. And here we have 21 inches in 24 hours, including a 9-inch per 3-hour subset out of that longer period, at least 20 fatalities. And the setup for this meteorology was a frontal boundary that had stalled out with low level airflow impinging on that boundary, triggering a complex of thunderstorms that just would not quit for a 24-hour period. Here is the rain accumulation map showing the extremely localized nature of the rain bullseye. And you're up in territories of 18 to 20 inches or so in this one small zone. You know, only a complex of thunderstorms is capable of delivering an amount and rates of rain on such a small geographic area like this. And here are some pictures, once again, showing the aftermath. The piles of cars, the shifted structures and homes off foundations, debris just strewn about everywhere, aerial view showing greater extent here. And here is, you know, the pictures just go on and on that show this type of domino effect of things piling up on each other. Here's the meteorological setup. So here is the frontal boundary that is stalled across western Tennessee. Here is the low level, very moist airflow. Ultimately, this airflow, I believe, derived from the Gulf of Mexico, impinging from the west-southwest. And within this scalloped area is where we had repeated generation of thunderstorm cells moving over the same locations from northwest to southeast. And here you see a satellite view, essentially looking at the same scalloped area. And this little brown zone here outlines this tiny, tiny little cluster of thunderstorms that is essentially anchored to one spot for so many hours. And that is what led to this catastrophic flood. Finally, we go to Birmingham, Alabama, October 6th through the 7th. And this involved the greater Birmingham metro area, 12 to 13 inches of total. And there was at least one recorded 3-inch per hour rain rate with 4 fatalities. The meteorology here, yes, another stagnant area of the jet stream, what we call a cutoff low, and a plume of moisture being drawn up the eastern side of that low out of the Gulf of Mexico, convective storms erupting within that plume. Here is a map showing the radar rain accumulation. You see Birmingham to the north. And once again, a very, very small concentrated bullseye of 12 to 13 inches of rainfall just south of Birmingham. Here are a few images that show this was mostly a nocturnal event. And, you know, that has its own societal difficulties with it in terms of getting warnings out, in terms of people having lack of situational awareness with where to go, what to do, and so forth. It just compounds, you know, the immediate phase of the event itself. Here's the meteorology, and here you can see this enormous vortex in the jet stream, the cutoff low, parking itself over the central plains, and on its eastern flank is shown in the pink here is that plume of Gulf moisture with embedded thunderstorms. And this is a few hours after the flood, but imagine everything shifted towards the west a few hours previous, and you would see that plume with training thunderstorms moving over the same locations. And so that's kind of my whirlwind tour of six events, and some of them had absolutely phenomenal rain rates, record-shattering rain rates. We look at China, we look at the event in Italy, that's very, very recent. And so what can we synthesize from all these events? And in terms of the meteorology, yes, there's a lot of variation in the large scale or the synoptic setup between various events. I would say the common thing was the presence of some type of low pressure vortex that was pulling in a plume of high moisture air off of warm nearby water. But these rain rates in so many of these events and 2 to 3 plus inches per hour and much higher in some of those events tied to convective cells. And the reason for that is convective cells contain an updraft, which is a core of rapidly rising saturated air that is sourced near the surface. And those updrafts draw from a large area surrounding the convective cell. So these cells are sucking in high levels of humidity from a great distance around the cell, and it goes straight up. The air becomes quickly saturated, condenses, and what you end up getting with a strong updraft is a very large, what we call mass flux, which is in terms of, kilograms per second per meter squared straight up. And all that moisture is going to get condensed and processed into rain. That's where you get your super high rain rates from, folks. You're not going to get this from a garden variety synoptic system in and of itself. The other thing about convective cells is if these convective complexes become persistent, and there's two ways that can happen. Either they can barely be moving or stagnant or stationary, and that is because the upper air flow is weak. The more common case is that these cells are doing something called training. They're moving one after the other over the same locations, literally like a rain train. And so what you get are discrete pulses of rain that come every 30 minutes or so. Myself and Andy Miller and some of our grad students, discovered that this was the case with the Ellicott City floods. There was a pulsing nature with 4 to 6 discrete pulses that occurred over several hours. That's certainly what happened in Italy. That's almost certain what happened in China, Birmingham, and with Ida. It's probably the most common modality for delivering high amounts of rainfall in a very short period of time. Let's see here. Let's go to the next slide. A little bit more now about the possible climate connection, and this is the topic that I know a lot of you are interested in hearing about. And I want to draw your attention to the very recent release, the 6th IPCC, which is the Intergovernmental Panel on Climate Change report, came out in 2021. This is a periodically released grand synthesis of knowledge from thousands and thousands of climate scientists around the globe working together to come up with these syntheses. And the latest one underscores the notion that for each 1 degree Celsius rise in temperature, the water vapor content of air increases by up to 7%. Now, I do want to point out that there are others that say it may be a bit lower. It may be somewhere between 4 and 6%. So there seems to be a little bit of disagreement, but there is a really strong nonlinear relationship between air temperature and vapor content. And this is what this diagram over here is showing. This is something, it's a graphical representation of an equation we call the Clausius-Clapeyron equation. This is something we introduced to all of our physical geography students in 110, and then they get it again in GES 311, weather and climate, and certainly in the classes that I teach. So we have surface air temperature on the x-axis and vapor pressure, which is a measure of humidity content in the atmosphere on the y-axis. This is what we mean by a nonlinear relationship between these two variables. And as you get up into the higher end of the temperature range, now this is degrees Celsius, you start to pick up a real increasing nonlinearity in the evaporation rates. And so the saturation vapor pressure of air becomes significantly larger for each increment in temperature increase. And so as the planet warms, we start to climb up the steeper portion of the response curve. And that's why I wanted to show this very important diagram. Now, what this translates into, all the things being equal, not saying anything about the degree of the instability available to these thunderstorms, the higher vapor contents feeding into the storm cells increase the mass flux of rain that will be generated and that will fall out of these storm cells. The storm cells become more efficient rain producers. They're working with more raw material per unit time. And now another important thing I want to point out is that in this water vapor is a tremendous amount of energy. And with an increase in water vapor, there is more latent heat being released as that vapor condenses. The amount of latent heat, I didn't put it here, but it's 2.5 times 10 to the 6 joules per kilogram. That's the amount of heat energy per kilogram of vapor that condenses. This is energy that warms the interiors of these convective clouds, folks. It's like going up on a hot air balloon and you're going to turn on the burner and you're going to put more warm air inside the balloon. It's going to rise faster. And that's exactly how the updrafts are responding. You put more energy into the cloud, you get a stronger updraft, which is going to increase the mass flux, which is going to increase the rain rate. So a lot of people talk about the air is more humid. Yes, but it's also important to look at the corollary that more energy is being released as well. So those cells become more intense. The other thing I want to mention here is several of these cases, as I showed you, had stagnant patterns in the jet stream, slow moving or stationary cutoff areas of low pressure, big meandering vortices in the upper level flow. This is a highly amplified jet stream. And Andy Miller and perhaps a few others of you know where I'm headed with this. There are several scientists that have written some papers about how the jet stream flow may be changing in the mid-latitudes. Jennifer Francis, Michael Mann, there are others, these are fairly prominent climate scientists, that with a reduction in the temperature difference between the poles and the equator, that has been happening. We know the poles have been warming up a lot faster than the tropics. We call this Arctic amplification, and it's related to the negative feedback between, the positive feedback between ice loss and decrease of reflectivity, increase in absorptivity of darker surfaces in the polar areas. We call it Arctic amplification. The jet stream derives its energy from that crucial temperature difference between the pole and the tropics. And the argument goes that with weaker thermal gradients, the jet stream should be slowing down a bit. And some of the folks listed here have demonstrated this with decades of weather balloon data, that yes, there's up to a 10% reduction in the average speed of the jet stream. And when the jet stream becomes weaker, it tends to more easily develop meanders. And by meanders, I mean loops. So the jet stream becomes a bit more loopy. It's not the straight highway running from west to east at high altitude around each hemisphere. And the loops include troughs. They include ridges that become more amplified. Some of those troughs can pinch off into cutoff lows. And so what you tend to see is perhaps an increase in these type of setups. perhaps there is an increase in the frequency of these large, high amplitude, more stationary patterns in the jet. And so that's a question I'm just going to leave open, but I think there may be some evidence pointing in that way. Now, there's plenty of evidence, I believe, out there. There are a lot of papers, and this particular set of data I'm showing here comes from a Climate Central research brief that was done in 2019, looking at 244 different cities in the United States going back to 1950, ascertaining the rain records to the greatest extent possible, and then binning rainstorms into 1 inch or more, 2 inch or more, 3 inch or more events. And what you see are some pretty holistic increases that are across several decades. More U.S. downpours, in essence, more intense downpours. They're becoming more common across the United States. And, you know, it's you see it across the board for all different levels of rainstorm. So I think that's some pretty strong data. There are other sources I could have shown, but for the sake of brevity, you know, just holding off. And this is a very important figure that came out of the 2021 6th IPCC from this summer. When you look at heavy precipitation over land, and we say this is what's called so-called 10-year event so this is a 10-year return interval type of rain event. This is what the IPCC suggests we are looking towards as we get into future levels of warming in the 21st century. These 10-year events are likely to increase by several factors. Again, the greater the degree of warming we experience, the greater factor increase in 10-year events. And so I think this is a nice graphic that sums up where we potentially could be heading. You know, if we just take the middle of the three values, a 2 degrees Celsius rise in the future, almost a factor of 2 increase in these so-called 10-year heavy rain events. And one can probably extrapolate this to even longer return interval type of events, I suspect. So with such devastating floods, how do we better warn people? So we're going to finish up here. And the prediction of heavy rain, folks, is more challenging than you might think. The models that we use have become quite sophisticated. And there's been a steady improvement in the physics in the models, in the granularity of the models, and as we can start to resolve down to smaller grid spaces, and we have faster supercomputers, and we have more and higher quality data feeding into these models. Yet with all these advances, we are still relatively constrained when it comes to saying today, here's where we think a flash flood might occur. The best we can do is portray a general region, perhaps several thousand square kilometer region. Somewhere in this box, this is where the models are suggesting there could be one or more flash floods. And the time window for those, not much better than 6 to 12 hours, okay? And so we can issue very strongly worded guidance saying, look out, this is a susceptible area. But the exact location of a flood, folks, a flash flood, and I cannot tell you a priori based on my model guidance, where exactly, what county, what part of the county, what hour this is going to initiate. We almost cannot do this until the event essentially is underway in the early stages. In other words, the thunderstorms have started to develop, they've congealed, they're clumping together, they're not moving. Uh-oh. Now we become kind of in a nowcasting mode, and it doesn't give people much lead time. It really doesn't. And the problem with this is that individual convective cells, we still cannot resolve those very well in our models. Maybe someday we'll get there, but it's too computationally intensive to do that at this point for all the United States. So there's the physical science problems on the one hand, and then there's the social science problems on the other hand. Rainfall is notoriously difficult to get people to understand. It can turn quite deadly on a dime, the flip of a dime. And there is a real need for more effective risk communication to raise the public awareness of rain as a serious hazard. So we have social scientists that are now working alongside physical scientists. My own grad student, Rhonda Plofkin, who's on this talk, who just joined my team, she's starting to look at these type of issues where there's the intersection of social science and physical science. How can we do a better job at warning for severe weather events? Okay. See, most rain events, folks, are quite innocuous. 99% of the time, your experience with a rainstorm is that it causes no problem, it's beneficial, and it does not inspire fear like a tornado or a hurricane. It does not. So there's a whole different psychology behind getting people to perceive the risk. And so the National Weather Service recognizes this, and the entire advisory / watch / warning system is getting a very serious overhaul right now. And it's taken many years, but it's forthcoming. We have too many types of messages, and the types of messaging categories are confusing. And now we have need to come up with a whole new warning, which is called a flash flood emergency. And this is very recent, just the past few years, to distinguish from flash flood warning. The flash flood emergency conveys life-threatening conditions are underway. And Ellicott City was the recipient of flash flood emergency during, I think, the 2018 event. Several of these events that I discussed in the United States, New York City, the Nashville flood, received flash flood emergencies. This is the absolute highest level you can communicate to the public. And before we even issue flash flood emergencies, we try to really look at the next 24, 48 hours and identify, hey, tomorrow is going to be a high risk day. And we were able to convey this for the New York City flood 2 to 3 days in advance. We had enough model guidance to suggest that there was the possibility of life-threatening floods across parts of the Northeast. And this is an interesting set of pie charts that shows, this comes from Alex Lamers at the National Weather Service, that these high-risk days, when they are issued, account for 41% of flood-related fatalities and 92% of flood-related damages, in spite of the fact that these are not issued very often. They're very rare. And so if you're in an area and you hear you're under a high risk for flooding, it's a big deal. You've got to pay attention to that. And this was issued in advance of Ida, for instance. Yet we had 57 fatalities. So we have to understand better how 57 people managed to perish when the risk assessment began 48, 72 hours in advance. And I think there needs to be more emphasis on conveying, when we talk about an extreme rain rate, this is what we're talking about. And it is a life-threatening situation. And I think that 3.2 inch per hour cloudburst over Central Park really caught people by surprise, even though they knew they were in a high-risk scenario. There was still an element of surprise there. Okay? And we also have the problem of what's called dual fuse warnings. A lot of times when you have flash flood warnings, there are also tornado warnings that are being issued from the same set of thunderstorms. And there's a study that just came out that shows how often this happens. And so what's the messaging for people? You're giving conflicting information. What do you do in a tornado? You go to the lowest part of your home, put as many walls between you and the tornado. What do you do in a flash flood? Get to higher ground. What the hell are you supposed to do when both these warnings hit your location at the same time? So these are all amazing problems for the people like the Ron Depofkins in the world to start looking at and tackling. Here's my final slide, final thoughts. Flash floods, folks, number one most common natural hazard of all the natural hazards. Every state in the United States has experienced flash floods. They are uniquely multifactorial, and I've brought back my diagram here once again. And because they're multifactorial, they are extremely challenging in terms of mitigation, prediction, warning, recovery. You've got to bring in so many teams of experts, and they got to be able to work together at this vent intersection. Okay. As you can see, there are still major barriers that remain regarding effective warning and effective response. And I've illustrated here, this is what I've focused on in this triad of factors here. Warmer temps translating not just to more rain, but overwhelming rain rates, and this is due to convective cloud feedbacks, and perhaps more and more of these stagnant large-scale flow circulation patterns. Folks, we're on a trajectory of increasing flood disasters and catastrophes worldwide. Remember, every natural disaster, every catastrophe is the intersection between physical factors and societal factors. Okay? We increase our urban footprints. We increase the amount of impervious surface. Look what happened with Hurricane Harvey, 2017 in the Houston area, 63 inches of rain in that event. That's a U.S. record. And Houston became a lake. And a lot of that was due to the fact that so much of that incredible prairie grass had been replaced by rampant suburban sprawl with no zoning regulations in place. There's a lot that we are accountable for in flash flood vulnerability. We as humans, land use change, climate change, the list goes on. Okay, folks, I'm going to go ahead and quit here. We have at least 12 minutes left. I'm going to unshare, and now I can, hopefully you'll see me a little larger, and I can see individual people. We'll go ahead and take questions, whoever wants to moderate that right now.
So thanks so much, Jeff. That's a pretty amazing story that we're dealing with here. So I'm going to ask people to post their questions in the chat, and then we'll call on you and ask you to unmute yourself and ask your question, and Jeff will answer it to the best of his ability.
We already have a few questions in the chat here.
Well, those are mostly comments, although Kim Grove did ask Kim, is that a question you want to ask, or was that rhetorical?
More rhetorical.
Yeah.
But actually it does get to the heart of it, which is when you are seeing these increased storms being increase of intense storms being I think, let me just make sure I wrote this down right. 41% of the flood related fatalities and 92% of the damages.
Yeah.
You know, how do you try to prepare for that? And this goes against the grain that we usually have done as engineers, which is trying to design for that, 85th or 90th percentile storm. But does that really help us for the thing that's going to cause the flood and cause the catastrophe?
Yeah, and I think it's kind of the assumption that all of their factors have been stationary over the past several decades, and I think the higher magnitude events are definitely becoming more common. And so does the envelope curve for the design have to shift with that? And what's the cost increase that's associated with that? What's the risk benefit equation for engineering? But I also will say that some of it is, for instance, New York City. People who don't have a mortgage, who are living in rented facilities, who are poor folk, often end up in death traps of places to live, such as these basement units where 13 people perished because they had literally no way to escape the rising water that came up to their ceiling. How does you'd have to eliminate all those types of dwellings in an urban setting. So I think it's beyond engineering. It's a societal policy issue that's been going on for many, many years. Same thing happened in Rockville, folks, a few weeks ago. Well, maybe more than a month ago. There was a horrific flash flood, Rockville, Maryland, and there was one fatality because of a person that got trapped in the basement of his or her dwelling, had no way to get out. So right here locally, this has happened.
Yeah, I see a question from Matt Fagan. Matt, do you want to ask that out loud?
Sure, fascinating talk, Jeff. I was just thinking, you know, like you were saying, people's instinct is to go into their homes to be safe. It's the exact opposite of what they should do if their phone was flooded. And I'm wondering, you know, it's usually incredibly rainy and nasty outside, so no one wants to go outside. But could folks interpret flood warnings a little better if they were aware their homes were not flood safe and had some knowledge of, you know, how much time, like when water starts coming in your door, how long do you have to leave, given a certain rain rate? I'm wondering if that could be incorporated into these warnings, you know?
And, you know, I think that's, you know, a lot of people don't realize that they live in a flood zone. They live in a flood prone zone. It was never conveyed to them when they rented or bought the property, or it just hadn't occurred to them, or it occurred so long ago that it's kind of left memory and so forth. You know, this is one of the questions Ellicott City is trying to ask. What do we do with people when the sirens go off now, when the water is starting to come up on Main Street? What you don't want people doing is running out to try to get to their damn cars. Because chances are their car is a few blocks away and those lots turn into lakes, those streets are turning into rivers. You want them to go vertical. Get up, 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 up as fast and as high as you can. And I think there's very distinct signage now in Ellicott City that says as much. You know, this is what you do, and this is what you do not do when you hear that siren. So, yeah, Matt, having that kind of guidance in lots of communities, I think would really help.
So Charlie Kaler asked a question that I think is one that's worth exploring, and Kim had something to say after that. So Charlie, you want to unmute, make that comment?
Sure, yeah. I was just asking about the analytical rubric of the 100 or 500 or 1,000-year storm, how useful it is and how much it's shifting over time.
Yeah, and you know what I'm going to do is I'm going to ask my colleague Andy Miller, who's a hydrologist, to give us his perspective on this. You know, I was hoping he might be able to address a couple of these questions.
So I'll just say very briefly, because we don't necessarily know, but I'm very skeptical these days when I hear something exceeds the 1,000 year, you know, or 1 in 1,000 year probability on the NOAA Atlas 14 precipitation frequency atlas, because it is non-stationarity that's affecting us now, right? We know everything Jeff just told you, and we know from our own perspectives that, you know, if a storm happens twice in 2 years in Ellicott City, that doesn't mean they aren't both 1,000-year events, but it means you should be suspicious as to whether they really are. And given the number of events happening in such close proximity, I think it's a real challenge. In terms of just things like a line on a map, such as the FEMA flood insurance rate maps, you know, my colleague Brian Bledsoe at University of Georgia had actually wrote a piece in the Washington Post back around the time of Harvey, pointing out that we just don't know how to explain this to people. We need different language to be used. Even FEMA is now saying things like, if you live, you know, in a 100-year flood zone, then you have like a 24% chance of being flooded in a 30-year mortgage. So, but as those probabilities change, it's a huge challenge. And a lot of people in Harvey were flooded who were living well outside of the 100, in some cases, even the mapped 500-year zone. So, yes, it's a problem.
Yeah.
And Kim wanted to add something, which is something that I think is worth mentioning. Kim, you want to unmute and just make that point?
Yeah, and this is something that we've been discussing a lot with MDE and the Maryland Insurance Agency, is that a lot of quote unquote flood areas or floodplains are associated with riverine and tidal flooding, but they're not addressing inland and pluvial flooding. And we're seeing increases of that, especially with these microbursts that you're seeing. And so you've got homeowners and home occupants who may not be aware of that risk that's in there. And we're trying to actually build a repository to kind of better understand where these things are, not only associated with the storms that we're seeing here, but also any other factors such as historic streams that have been otherwise piped that can be influencing how flooding is happening. And flooding is not just what's happening within the roadways. Flooding can also be when you're seeing damage within people's basements and structural damage.
Yeah, that's a very good point, Kim. I appreciate you raising that. And like I say, if someone is in a suburban or an urban setting, they're nowhere near a stream or a river, it may never occur to them just how extremely vulnerable they are. All it takes is a low spot in the road or next to that building to create a fatal event.
Couple that with debris accumulation within the collection system, and it makes it even more difficult.
Yep, exactly. Exactly. Very good point.
But several people have been commenting here on local zoning and poorly designed patterns of where people live that get because of drainage design. Chris Schumann made a point, and so did Yeva Christina Lysenko, both about improper drainage design. I don't know if one of you wants to unmute and say anything about that, or whether the comment just stands on its own. But we know that those kinds of things do exist as well.
Hey, Andy, it's Chris Schumann. The 1937 layout of Greenbelt, the historic Greenbelt, essentially led to this problem persisting since the place was developed. Kids of the original pioneers who lived here described this particular area as the swimming hole, and nothing has successfully addressed it. And the building that exists right now has the basement apartment units flooded out multiple times just in my relatively short stay here. And yet somehow the occupancy permits keep getting reissued. The last one was so fast that I believe they had to be rescued through the windows because the doors simply were not able to be opened. They were jammed by the water pressure. So hasn't killed anybody, but it has destroyed multiple families, existence in mere minutes, really.
I'll just add that this is something that the state is now not only aware of, but also has now a law that was passed in the last legislative session that mandates doing things like reporting on updated precipitation frequency estimates. There are projects that have been in progress that have actually started to develop ways to try to update those risk estimates, but the state is now mandated to put. The state was thinking about this already, but they're actively mandated now by a law in the legislature that passed in the last session that's now in effect to actually report on this more frequently and make plans to deal with it. And it's a very difficult problem for a whole bunch of reasons. Okay, does anybody else have questions or comments? Well, it's now 1 o'clock and I haven't heard anymore. So Jeff, I think we're just going to thank you for a fascinating and very enlightening presentation. I will let everybody know that we are going to post this on the YouTube channel of the Center for Social Science Research, and we will actually publicize how people can get it if they weren't able to attend today. So thanks, Jeff. Thanks, Tyra, for your help in co-hosting the seminar.
Thank you very much for having me. And those of you who are in my class who are present today, thank you for attending. And we'll make sure you get access to the link.
Okay, I'm going to stop recording now.
Okay. Take care. Bye-bye.
Bye-bye.